uncertainty. To summarize this entire chapter in one line, I would say measurement errors in all experiments makes understanding uncertainty super important. Let that sink in for a little bit. Measurement errors in all experiments makes understanding uncertainty super important, because we're going to use the language of uncertainty to describe these measurement errors that are bound to be in every experiment that we run in real life. So that's why this chapter is important. There are a few key takeaways in this chapter, but a lot of topics are advanced. But if you get this one line as to every time there is a result of an experiment, there is bound to be uncertainty because of the errors that exist in just measuring. So let's get into it. So the key concepts we will cover in this chapter are 5. 1, we will understand why in detail understanding uncertainty is important. 2nd, we will look at 2 different schools of thoughts and 2 different ways in which uncertainty is described, the Frequentist method and the Bayesian method. And then we'll look through a real life example of how we can use this and describe uncertainty in Frequentist method and Bayesian method with a simple example of a coin toss. So we'll use a real life example, make it real. We'll understand why bootstrapping as a technique is important, where we can use ways to simulate and run experiments with the data that we already have and not have to run real life experiments. Then we will understand multiplicity as to what is that problem of multiplicity and how we can solve it with FDR, with false discovery rate. So I would say only the first topic is really important from a practical standpoint. There are lots of details in advanced topic. And so what I have started doing is I've used this emoji, which is like this. It says, hey, it's going to make our brains work a little harder. So in any slide at the top left, if you see this emoji, that's a sign from me that tells you that there are some advanced topics that this video will not do a good job. What I'll certainly do is I'll send you some more links in the description of this video where you should go in detail with those topics. I personally got a lot out of those videos and I learned from it and some of those external content. So I will paste those links in the description. But you are warned that these topics, some of these topics with these slides are going to be advanced. And as long as you understand the heart and meaning of some of the key concepts, that's sufficient for you to practically use it. All right, so that's the overview. Now let's get into the detail. First one, why is understanding uncertainty important? So I'm going to draw one by one each of these bubbles and explain to you, okay, why is uncertainty important, right? So for not just for us to understand uncertainty, but use the language of uncertainty, yeah? So in real life, we run experiments. There's lots of natural phenomena that occurs, like example, people buy on Amazon. That's a phenomena, right? And you want to, these phenomena are interesting because from a business standpoint, you want to understand those phenomena as to what drives people buying more or less, and many such things that you do in real life where you want to understand how your business works. So that is a natural phenomena as to how people are using your goods and services, and you are really interested in understanding what's driving those behaviors, right? So you form a hypothesis that says, hey, these are the things that I know about what's really good at buying at Amazon, like the instant delivery, like less than 2 days, you get your products at your doorstep. It's highly convenient, easy returns. So these are all hypotheses. You believe that easy return helps describe the ease with which people use Amazon describes how Amazon is successful. So you want to understand how your company works. So you form various hypotheses as to what you know. There are certain things that you know which are that are important for your customers. You can run surveys that says, hey, ease of shopping, mobile interface that's intuitive, UX is better. So these things that you want to understand about this natural phenomena via your hypothesis, I would call them the targeted unknowns. You don't know how much these factors impact the volume with which people buy on Amazon, but you know that these are unknowns, but I want to know about them. So these are called targeted unknowns, and you want to know about them. So what you do is you run experiments, and these targeted unknowns are what you use as your parameters of that experiment, saying, hey, I'm going to watch for this metric, this unknown of if I, let's say, were to increase the delivery days for a certain experiment from 2 days to 4 days for a long period of time. So that's my targeted unknown, and I'm going to watch its impact on the sales of Amazon. So you run experiments. That's the third step. You form hypotheses, you figure out certain key metrics that you're interested in, and then you run experiments. Then when you run experiments, what happens? You gather data. You collect the result. This gathering the data is where there is always going to be a measurement error. An error in measurement where what your results tell you will only tell you a part of the story. Because there are so many things going on when someone's making a buy decision. Maybe their location of their home is way far off from the nearest store. That's the most important factor. You didn't even think about them. So, and those are the untargeted unknowns, right? So when you run experiments with these parameters, there are targeted unknowns, but there are unknown unknowns which you cannot model and you cannot target them. And so your experiments at best will tell you about what are the targeted unknowns and how they're moving. But there will be a measurement error because there are unknown unknowns that could be going on that you didn't think about, that's important for your customers so that they buy more on Amazon. And that's just one reason why you have a measurement error, but you can imagine so many reasons why there could be a measurement error. Measurement error could be because the result that you capture by the tool that you use is faulty. Maybe it's supposed to count 10 successful orders, but it only counted 9. So there's so many reasons why there could be an error in the tool, error in skipping certain unknowns that you should have factored in. And so your measured value will always not be equal the true value. So when there is a measurement error, when you run experiments, you gather results and you have an error, this is when your captured results require this language of uncertainty to describe these results. You have captured your results, but this is where you use the language of uncertainty to explain as to what is your captured result actually telling about your hypothesis. As to this hypothesis explains this natural phenomena with a certain level of confidence, with a certain level of ambiguity, right? So that's where understanding that when we run experiments, when we gather data, that there's bound to be an error, and there's supposed to be a way in which you can explain that error or uncertainty that's baked into your results that you've captured. So that's why this chapter is important. If you understand this, this is the heart of it. And this starts with that one-liner that I shared. Measurement errors are part of all experiments, and due to which we need to explain the results that we have with the language of uncertainty. So that's what we shared, in summary as to these errors. We need a way to quantify how stable is the captured result and how uncertain it is, right? So there's this stability part and there is the uncertainty part, and both of those things are equally important for us to scientifically scientifically report our results, right? And so this is where uncertainty comes in. There are two schools of thoughts in which how uncertainty can be described and approached: frequentist approach and Bayesian approach. A frequentist, in a sense, starts with a hypothesis. It says, hey, if you make delivery faster, then that will lead to better results. So they start with an hypothesis and then they interpret the observed result. And then they run several repeated trials, they build models and use parameters to reduce false discovery rate. They use various techniques like the bootstrapping to simulate running those experiments without actually running them, and FDR techniques, which we'll go into later, to reduce false positives. Frequentist is what that I described, but Bayesian is, they start the opposite way. They start with an observed result and then they talk about how accurate is this hypothesis. So if you look at it, how you start is, I think, the key distinction between these two. One starts with an hypothesis and talks about the observed result. The other starts with an observed result and talks about the hypothesis. The other key distinction is that Bayesian allows you to combine your prior beliefs with data. So you can say, hey, I believe that based on like some historical evidence that when Walmart first did it, that they were closer, they delivered faster, they had some experiments. So I'm going to use that as my prior assumption. So you can, and that's your belief. You can combine beliefs with data with the Bayesian approach, and you can say, hey, these are my probabilities as input. You can't do that with the frequentist approach per se, but we'll go into the detail. So those are the two ways in which you can describe this. And typically in an ideal setting, which never happens actually, in an ideal setting, you want to be non-parametric, meaning you want to not assume any thing about your variable, no assumptions about what are your functions, no prior beliefs. All you do is you run lots of experiments and you accumulate enough data, and then your prior beliefs are no longer needed because you just have all the data and you work through it. And so your model is non-sensitive to those beliefs. But typically, first, you cannot run experiments thousands of times. It's expensive. And so you have to have certain prior beliefs. You have to get really good at understanding your business use case and then bake that into your experiments. And so Bayesian is what typically a lot of real life examples really require you to do, because you have to start with certain prior beliefs. You cannot run experiments so many times. Yeah. So that's the summary of this entire chapter. Every topic going forward will have this this emoji on the left. These are all advanced topics, and I've done a little bit to go one level deep, but they require detailed study in themselves. So now I'm going to go into the depth of frequentist and Bayesian, and then I'm going to look at a real life example. All of the topics going forward are going to be advanced topics. But what I have done is I've tried to make it simpler to understand in a sense. But the caution I have for all of you is you would have to do a lot more study and get really good at statistics to understand all of these concepts that are described. You have to get really good at understanding the computer algorithm that each of these techniques use. But if you understand the heart of it, that is sufficient as a practical user of these techniques. So as I said, there are two ways to describing uncertainty: the frequentist and the Bayesian. The frequentist would say, hey, given the hypothesis that the coin is fair, let's say you have a coin, you toss it 5 times, and then each of those 5 times it gets a head. Each of the 5 times you get a head. And so how would Frequentist describe it and how would Bayesian describe it? This is how I'm using this slide. You have a coin that you tossed 5 times. Each of the 5 times it turns out to be a head. So the frequentist would start this way. He would say, given the hypothesis, it'll make a hypothesis that says, hey, the coin is fair. Let's start with the hypothesis, yeah? And then it will say, how unusual is the observed result? Getting 5 heads in a row. So they make no assumptions. They use lots of data, build complex experiments, even potentially models that overfit, and that's what they do. And they'll describe like, hey, how to describe whether the result is unusual or not. They just start with the hypothesis and describe the result. Bayesian, on the other hand, if you come to a Bayesian uncertainty school of thought person and you say, hey, I just tossed this coin 5 times, every time it landed a head, what would they do? They would say, hey, given the observed result, they start with the result, not with the hypothesis. They see the frequentist started with the hypothesis, the coin is fair, and then they're going to interpret the result. Bayesian starts with the result, saying, hey, given the result, they assume the result is you got 5 heads in a row. Now they're going to look at probability. Frequentist, there's no probability. There's Bayesian would say, what is the probability that this hypothesis that the coin is fair is true, right? And so they make prior guesses. They know there's a 50-50 chance if it's a fair coin. So they make a lot of assumptions. So that's the key distinction. Where do you start and how do you describe the end result? Yeah. So now let's look at an example even more. I described in high level with that example, but let's go in even more detail how these two schools of thought would approach it. So if you have a coin tossed 5 times and it ended up with 5 heads in a row, you'd say, hey, frequentist. Let's start with the frequentist. Frequentist said, the question that they would answer is this: how unusual is the result? Start with the hypothesis. They talk about like, I'm going to interpret the result. Yeah. So frequentists would ask these type of questions: how unusual is the result? Yeah. And so what they'll do, they'll form a null hypothesis. They assume the coin is fair. They make no assumptions about like probability, none of that, right? They just say, hey, coin is fair is my hypothesis. And then they calculate the probability of 5 heads in a row under the null hypothesis would be 1 by 2, which is 50% of the time. If you toss a coin, you get heads, and you raise that to the power 5, so meaning 3%. And so what they do is they say, hey, assuming 5% significance, alpha of 0.05, when we do that, it's a fair assumption because 95% of the results would lie under 2 standard deviations of alpha of 0.5. Meaning, if this observation is outside of it, meaning in this case the p-value of 0.03 is less than, we can safely reject the null hypothesis. So what they're saying that the coin is fair. They're saying I can reject the null hypothesis that the coin is fair. So they would say it's highly unusual to get this result. Yeah, they say this is highly unusual to get this result. But does that mean that they would say that the coin is a fake coin, both sides head? No, they'll never go into that area. They'll just talk about the result. They'll say it's highly unusual that you get 5 heads in a row. They focus on interpreting the result. They do calculate probabilities, both do, but then they focuses on using probabilities in this case to describe the result. Now let's see how the Bayesian would approach the same thing. The question that they would ask is completely different. They would say, what is the probability that I have a novel coin? That's the question. Yeah. In this case, they assume it's a fair coin. They're just saying, I'm going to calculate the probability that I have a novel coin. So assume that, and then they have certain assumptions and beliefs that bake into it. They just say, hey, the chances that you have a novel coin or a coin that is both sides head, in this case novel coin is not a fair coin, is 1%, meaning it's a very low chance. They just give a 1% threshold. And so then they calculate probabilities for a fair coin, which is 99 times 1 over 32, right? So they say, hey, this is 3.1% chance. 1 over 32 is 1 by 2 raised to 5. Yeah. So they do the same, 1 by 2 raised to 5 times 99%. They are calculating, multiplying that by 99%, because in their mind 1% is a fake coin or a novel coin, and 99% is a fair coin. So 99% times probability of a fair coin, which is 1 by 2 raised to 5, which is 1 over 32, and that's 3.1%. So they say, hey, I'm assuming it's a fair coin, it's 3%. Assuming it's a novel coin, I've given it a chance of 1%. So the total probability of this event of, it could be a fair coin or it could be a novel coin. So I'm just going to add those two probabilities. I get 4.1%. So 3.1 plus 1, because there's only two ways in which this coin could be. Either it's a fake coin or a novel coin with both heads, or it's a fair coin where it's a heads and tails. So they calculate the probability to come up with a 4.1%. Yeah. So the probability of this event, which is basically it's a novel coin, is 4.1%. So the fair coin probability is 3.1. The total probability divided by total probability. So that's a fair coin is 3.1, which we got here, divided by 4, which is 76%. The chances that this coin is fair is 76%, right? And heads on a novel coin probability is 24%. So they're saying this is a fair coin, right, in some way. So but they'll never say it that way. They say, hey, the probability that you have a novel coin heads only is only much lower, 24%, than being a fair coin. So they would get you a probability that says, hey, this being a fair coin is 76%. It's a novel coin is 24%. It's the same thing these guys are saying. It's highly unusual to get 5 heads in a row, right? So so these are two ways, right? So he's saying, Bayesian would say probability that you have a novel coin is low. So that means you have a fair coin, higher, 76%. And so here they're saying it's highly unusual to get the result 5 heads in a row. And so they assume it's a fair coin. And it's very different. But imagine if you had given this as a 5%, then you would have come up with a completely opposite result here, right? Here, if you see, under this assumption, it's highly unusual, right? So they are saying, a frequentist in this left case is saying that it's not a fair coin, right? Here it's also saying that it's not a fair coin. It is a fair coin in this case. In this case, it's saying it is a fair coin, right? So there are two different results in this case because of this prior probability. But if you make this 5%, that it's a novel coin chances of 5%, then you will get the same result as a frequentist, right? In this case, they don't agree. But based on your prior probabilities, this is where understanding the business use case and understanding the probability of what's really going on in your business has a huge role to play in a Bayesian. This result would completely flip if you change this to a 5%. Like this prior probability to a 5%, and that would change completely, because this would be, 3.1 plus 5, right? So that would be close to around 8% total probability, right? And then if you do 3.1 divided by 8, right, it's going to be a lower number than the novel coin probability. So you see, this has a huge role. Input probabilities has a huge role to play. So now this is another topic, advanced topic, bootstrapping. Basically, it's a technique in which you can, running this heads, tails coin experiment is easy. But let's say you really wanted to run this experiment on Amazon and delay, let's say, the delivery of your goods and services. Can you run that experiment like thousands and thousands of times? Maybe you can, but certain experiments would be very expensive to run. So can we do something with use of statistics and data and algorithm to not have to run all of these experiments so many times? So yes, that's where the technique of bootstrapping comes in. In a sense, you have a single run, an experiment, and you do sampling, resampling with substitution, and that's a much closer representation of reality, of what your true results is. So there's a, if you understand that, in a sense, bootstrapping allows you to sample and calculate your interested metric. In this case, you could say, hey, I want to calculate the confidence interval, I want to look at my estimated error. So with the sample that you have, you again resample several times, and you do substitution. You allow substitution of sampling of the same data point. Then you plot a histogram. When you plot that histogram, that's going to be a better representation than your original sample. And when you run a statistic on that histogram, you get a better, stabler result that you can interpret. And Bootstrap helps with that. There's a very detailed video by StatQuest with Josh Stammer, and it's in the description too, that gives you a lot more detail and a visual understanding of bootstrapping. But if you understand this key concept that, hey, you have a certain set of results, and instead of interpreting just that results, if you do sampling and resampling on the same set of results with substitution, you get a different histogram. And if you run a statistic on that, that's going to be much more closer to you. It's as if you simulated running so many experiments, because you just use data that you have in different combinations. That is sufficient. That is what bootstrapping, in a sense, is. Allows you to simulate and run multiple experiments with the same data. The other topic, the last topic, is the problem of multiplicity and how we solve it with false discovery rate. So let's say you are in advertising business, yeah, and you are trying to find out what is the signal that there is a future purchase intent for this user who I'm trying to show an advertisement. So there's going to be very low signal and lots of noise, because there's going to be thousands such things that you'll be tracking about this person, and very low chance that you can get signal out of noise. And so this is where problem of multiplicity comes in, because what happens is we conclude p-value when it's, let's say, 5%, alpha 5%, because it's 95% of the results are in less than 2 standard deviations. This is true for one test, but if you run this test and use this relationship between p-value and reliability of your result, and you run this over many times, like in this case I talked to you about digital advertisement, there's going to be very less signal. And so what happens is your false positives start to become more prominent, and they become significant. You start to feel that there are certain parameters and features that are actually significant, but they're actually not, because they are false positives. And so there's this technique, an algorithm that you can use called the FDR control, or false discovery rate control, by Benjamini-Hochberg algorithm. In a sense, it reduces this, it tries to get the signal more out of noise, right? And it readjusts your p-value from being significant to not being significant anymore, based on an algorithm that it uses. So if you understand this, and if you have a use case where there is low signal and your experiment, you're running this over and over time, many times you're running, then you have this issue of false positives becoming significant, and you start to make decisions based off of that. And when you run this multiple times, that's the problem of multiplicity. The single test relationship between p-value and reliability breaks. So being aware of this is equally important, and using techniques like the Benjamini-Hochberg algorithm helps you reduce false positives. And you can, and the technique is called false discovery rate, reduction false discovery rate, right? And again, there's a really detailed video in the description by StatQuest with Josh Stammer. I've been a big subscriber and watching a lot of videos that were very helpful. Again, this is advanced, but if you understand the key concept of why this is, then this slide should do the needful. In the next video, we're going to look at chapter 2. So this concludes chapter 1. Yeah, we covered several topics, 5 specific topics that we went over. Were why and where uncertainty becomes important. We understood that. We understood 2 schools of thoughts, Frequentist and Bayesian. We understood with a real life example of costing a coin toss with 5 heads. Understood how we can do simulation with 1 data set with bootstrapping. Understood when false discovery rate can be used. We can reduce false positives with FDR, Benjamin-Hochberg technique and algorithm. But if you just remember this one line, that is it. Understanding how you interpret your results, right? Because there's going to be measurement error in all experiments that we run for various reasons that we went over in this. And so understanding how we describe that uncertainty is super, super important. All right, I will see you all in the next chapter. Thanks.